Hey everyone, welcome back. This video is a continuation from our last K.5 video that was introducing the idea of analyzing a scenario that's happening both horizontally and vertically. What we're going to do in this video is actually look at kind of the reasoning why and how we are able to still use our horizontal and vertical motion equations, kind of a reasoning behind that. That's what we hope to cover. Okay, so let's go ahead and dive right in. This video is about understanding vectors, and while I am never in my own class going to quiz you directly on vectors, and there's never on the AP Physics 1 test going to be a specific or explicit vector question, it's important to understand what vectors are, how they act, to understand our approach as we get into projectile motion. Okay? Now, the thing that we're going to focus on is this idea of adding vectors. Just like you can add numbers, 5 plus 3 is 8, you can add vectors together. A vector, if you remember, is some amount and some direction. Velocity is a vector, some amount, 20 meters per second, and a direction, north. You could represent that visually with arrows, and that's how vectors are often represented. So here is a vector that I've labeled as A, vector A. Well, this arrow at this diagonal, I don't know, it's maybe, 20, 30 degrees above the horizontal. This vector is equal to, well, me adding up two other vectors. Again, not too dissimilar from the idea that a number is equal to the addition of a couple other numbers. Like 7 is equivalent to 5 plus 2, right? So this vector here, here's that same vector A, it's the same thing as B and C. When you add vectors, you always do this head-to-tail thing. So I take the tail of this vector C, I kind of slap it right next to the head of vector B. Okay, I line them up, and then the result is the vector that, again, is equivalent in this example to vector A. So you can add up vectors together. Put another way, this diagonal vector is equivalent to two vectors that are perpendicular to each other, B and C. All right? Now, why is that important? Because in our physics class, we focused on horizontal motion. We learned about vertical motion. But those are just two, frankly, specific examples. There's a lot of scenarios in the real world, in our universe, that are at some, say, diagonal, that are not only horizontal and vertical. So while we learned a set of equations for horizontal motion and vertical motion, man, I don't want to learn a whole bunch of equations for all the different possible angles that things can move. That's why we're going to take advantage of this aspect, this quality of vectors. I could have any angle vector I want. So I have this one labeled here as A. I already showed you. It's equal to these two added up. Here I have just at the bottom another example. Maybe I have a vector pointing up and to the left this time. It again could be identified or equivalent to the addition of two other vectors, one that's horizontal and one that's vertical. Any line that you draw, any diagonal that you draw on a 2D space can be represented by two perpendicular vectors, and they're equivalent. And that's nice because that means that we can still use our vertical and horizontal ideas and equations for any type of motion, for any type of vector, displacement, velocity, or acceleration. We'll mostly be focusing on velocity, but any vector has this property, all right? Now, if we always break our diagonals into the x and y, we don't have to learn any new sets of equations. Again, we already learned equations for vertical motion and horizontal motion. I don't want to learn a new set of equations for this motion, a new set of equations for this motion. Let's just stick with those two sets. And because we can stick with those two sets, we can use them for any type of direction. But it does mean that we're always going to be looking at not these different diagonals, we're always going to be looking at the y and x. They're known as components, those pieces. Okay? Now, why can we get away with this? Why can we always break them down and still just use those two separate sets of equations? Okay, you can't always do that, but you can if you're using perpendicular vectors because perpendicular vectors don't affect each other. Here's what I mean. Here I have some vector, this green arrow pointing to the right. It's a vector. Okay, it has some amount, some distance, some length, and it has a direction to the right. I could add to that another vector. Here's one that's in yellow. I add them up. Remember, it's kind of heads to tails. Okay, I line them up, and the result, what you're left with is, I don't have a ruler proving it, but this red arrow is the exact same length as these two added together. Now, this yellow arrow, because it was in the same direction, it changed our result in that direction, right? It affected it. This yellow arrow affected the length in that same direction, that starting direction that was towards the right. But I have another example. Let's say I take that same green arrow, but now I'm going to add a vector that's perpendicular, acting straight down, this kind of burgundy or maybe, I don't know, reddish-brown arrow pointing down. Again, I'm going to do this heads to tails method. So I draw one of the vectors. Okay, I put the tails of the second at the head of the first. And then the result is when you connect the heads and tails together. So what I'm left with is this one. If I could drag this arrow, it would go from here to here. That's what that is equal to. But this is crucial. I did not change that horizontal length. The horizontal component, this green component, it is still exactly there. It was unchanged. Even though I added another vector because it was perpendicular, it did not affect that first vector. This is not dissimilar to, if you remember our old video, our last video I should say, that vertical motion when that ball was falling, that falling ball, right, it accelerates because of gravity. It goes faster and then faster and then faster and then faster, but it will not affect the horizontal motion because those two vectors are perpendicular. So this is kind of a blessing and a curse. It's a blessing in the fact that, man, we don't have to learn all these different equations for all these different angles. That's fantastic, okay? It's maybe a curse because we always have to make sure we're breaking them down into perpendicular pieces, horizontal and vertical, because that's the only way we could get away with still using those two sets of equations. If we were trying to use non-perpendicular vectors, well, they might influence each other, just like these ones. This one influenced the green one, and you might need like multivariable calculus to deal with that. So we're going to stick with always looking at not the diagonals, but looking at the same horizontal and vertical, and then we can still use those equations that we learned already. Okay, so when we come across, and we're not going to do it in this video is just about over. When we come across motion at some angle, we're going to almost like ignore that angle and instead look at how that angle is represented horizontally and vertically in the x and y direction, the components in the x and y direction. Because, well, we're used to doing that. We've already done several examples and we've seen several videos, and it allows us to use those same sets of physics equations, and, oh my goodness, I bet you learned some right triangle trigonometry from your math class. Notice, these are all right triangles that I've been showing you. If I go back over like, right triangle right there, right triangle, right triangle. We know how to pretty easily solve for right triangle trigonometry. So if you know angles and lengths, you can figure out those components. Okay, and they're independent of one another. So especially for velocity, we're going to be doing this quite a bit. We're going to look at objects like, a cannon shot into the air or an object sliding down a ramp. They're moving at some angle, but we can just look at the x and y piece of that motion and use those same sets of equations. And we're able to do that because those vectors don't affect one another. So we can use those two sets of equations and keep them separate, and they aren't going to interfere with each other. That's it. That's what we're moving into projectile motion. In the next video, this is kind of the rhyme and reason of why we're able to do that. That's it. I'm signing off. Thanks for watching.